Welcome to Messi Pupin online course on basic principles and calculations in chemical engineering. So, we are discussing about fundamentals of material balance under module 3, and under that module 3 we have discussed the principles of material balance and their know-how for the calculations of the chemical engineering processes based on that fundamental principle of material balance. Now, in this lecture we will try to discuss about the material balances on the processes with recycle and bypasses. And so, previous lecture we have discussed the flow chart, labeling, a process flow sheet, general material balance equation, basis for calculation, typical single unit material balance problems. Based on those general material balance equation, we have given lot of informations, even we have done some problems how to do the material balance and in compound basis, total material balance, and how to that specify that stream by their quantity in terms of flow rate and also in terms of mass fraction or mole fractions. So, here also we will continue that material balance problems on non-reactive processes with recycle and bypasses. So, we have discussed that before going to that do the material balance equation, we have to specify the systems on which actually we have to do the material balance of the compounds or components or atoms and also total material balance there. And in the process flow sheet, how it can be that specified in the input and output streams based on their flow rate and also mass fraction and mole fractions there. Like here flow chart is actually discussed for the single unit, how that flow streams are specified by their quantity. Like here in the slides that in the mixer, that inlet stream and there will be two outlet streams or there will be that two inlet streams and one outlet stream. So, in the streams that how that components or that rate of that flow is specified there. It is already discussed in the previous lecture there. So, this is also for the multi unit system, that how that material balance can be done after specification of the that flow rate and mass fraction of the compounds that is flowing through the streams. Now, in this lecture we will discuss something about that recycle, bypass, even makeup, parts, what are those that process system for that to be considered for the expression of that particular processes. There, suppose recycle, here sometimes that in a process unit that some unreacted portions will be there in the outlet streams, and those unreacted or that extra amount may be reused for that process. So, it will be recycled to the use in previous unit where it will be actually utilized there. So, in this case, one example like this that for the recycle, unused material being cycled back to the feed stream, and in this case suppose there are three units, one is mixer, another is reactor and another is reactor 2. Now, in this case the feed is going to the mixer, where this feed will be mixed with that that unused reactants that is coming out from the reactor. Then this unused reactants will be mixed in that mixer with the feed mixer with the feed. After that this mixer will be sent to the reactor 1, and then after reaction in the reactor 1 that outlet streams of that reactor 1 will contains that some products as well as unreacted compounds of that reactor 1. After that it will be sent to the reactor 2 for further reactions. Even after further reaction, you will see that there will be some unreacted amount and some that products will be there. So the products will be separated and it will be taken out as a product, whereas unreacted that materials can be reused and it will be sent to that again mixer, in the mixer, that feed mixer will be mixed there, and then again it will be sent to the reactor. So these streams, that these streams will be that regarded as that recycled stream. Similarly, some process also will be in such way that some stream that skips one or more stages of another processes and goes directly to another stage further downstream. Like here feed is coming to one unit, process unit, it is called divider. Now in this case this divider will allow the streams divided into two parts. One parts of that feed mixer will go to the reactor, one for its process, and from that reactor it will go to that separator for the separation of the products. But whereas you will see that some feed mixers sometimes to process in this separator or some other units, some portions of the feed mixer required to directly send to its that process unit. Here it is sometimes required for maintaining that flow rate as well as that component at a certain amount there, and after that product will be coming out. So this type of process will be actually regarded as with the bypass process. So here in this case a stream that skips one or more stages of another process and goes directly to another stage further downstream for its processing. And special cases like purge, sometimes it is required. In that case a stream sometimes will be taken off or bled off from the process to remove and accumulated unwanted materials, or you can say that some inert materials that might sometimes otherwise build up in the recycled streams. So that unwanted materials as inerts materials that can be taken out from the outlet streams of the process unit there. Here in this case see feed is coming through the mixer and it will go to the reactor, and after that products will be separated into a product stream and unwanted materials. So in this unwanted mixture of this materials, some will be that used and reused, and it will be recycled back to its mixer here. But some inerts materials which will not be actually used for further processing, that can be taken out as a parts there. So this type of process also will be in the chemical engineering process. So how to do that material balance based on this that recycle, bypass, even parts, that will be considered here. Another, this makeup also, sometimes some amount of components will be shortage in the flow stream, so you have to give input as a makeup there in the stream. So a makeup stream is required to replace losses to leaks there. Sometimes there will be some leaks, then there will be some losses of that material. So to fill up those leaks or other carryovers, in that case that you have to give some makeup in the recycle loop. So that will be considered as a makeup here. Like this in this stream you will see that process with makeup streams here, that feed will be going through the mixer, along with that recycle of this separator here. And in that, whenever you are recycling that from the separator, you will see that some loss amount will be there, so that that particular flow streams will not be maintained. So there of course you have to give input as a makeup there to maintain that components here in the mixed stream. So after that mixing, then it will go to the reactor. Again that product streams of that reactor, it will be separated in the separator, and product will be coming out from the separator, and the unreacted compound to be recycled back to the mixer along with the makeup. Now if we recall that general material balance, we know that there will be some accumulation. That accumulation will be equal to input minus output plus generation minus consumptions. So this again general material balance equation will be used for calculation or you can say do the material balance based on that bypass, even parts, or that recycle processes there. and that these things we have already discussed. Even if there is no chemical reaction even at a steady state condition, then we can say that the final equation of material balance will be is equal to input minus output. So in this lecture we will also again that consider that non-reactive systems where that consumption and generation terms will be 0, whereas at steady state we will consider that accumulation will be is equal to 0. So simply we can do that material balance as input minus output. So as we know that the principles of that material balance, whenever you are going to do that material balance, you have to do either by mass or mole basis. So either one you have to follow, or you can do that material balance based on compound balance, or you can do the material balance based on atomic species balance. And whenever you are going to that compound balances, to solve those equations based on that compound balances, you need to have sometimes that total material balance. So you have to do also that total material balance. So we have already discussed all those things. Now here we will discuss the example with recycle stream. Let us have this example of separation of benzene and toluene in distillation column with recycle. In this case, suppose a continuous operation distillation column that operated at 1 atmosphere, which is to be designed as shown in figure in the next slides, to separate 13,620 kg per hour of a solution of benzene and a toluene that contains 0.4 mass fraction benzene, that will give you the overhead product that will be containing 0.97 mass fraction benzene, and bottom product will be containing that 0.98 mass fraction of toluene. Now in this case you have to write the overall material balance equation, write the overall benzene balance equation, and estimate the distillate and also bottom products. Now what will be the reflux per kg of distillate product to be used if the overhead product is 11,713 kg. So in this case very interesting that see this schematic diagram of the process here. In this case this distillation column is used, and feed is coming at a certain rate with benzene composition as XF, and after distillation you will see that the benzene and toluene mixture will be separated out, and from the top portion you will see that that heavy product, as that we can say that benzene will be coming out from the overhead of this distillation column as a vapor, and after that it will be condensed, and after that condensed that liquid benzene will be that collected as a distillate. Now from that condensed or the liquid distillate portion, you have to some portion of that liquid benzene you have to send back to the distillation column for the process. Now that is called that recycle of that distillate here in the distillation column. So this some portion should be taken out as a distillate, and some portion of its vapor phase as a liquid form, it will be sent back to the distillation column. Whereas in the bottom that from the bottom the liquid that toluene will be taken out as a an amount of B, and there will be some composition of this B there. Now in this case since it is a recycle problem, you have to do the material balance, and also that you have to do the overall benzene balance equation, and also from that you have to calculate what should be the distillate and what should be the bottom product as B. Now in this case what should be the overall material balance? So we know that basic equations of the material balance, they are that accumulation will be equal to input minus output plus generation minus consumption. Now in this case since there is no reaction is going on, so you can simply omit that consumption and generation terms, and also since this is a steady state operation, also you can neglect that accumulation term. So finally it is coming as input will be equal to output as per equation. So overall material balance, if we consider that as an input what will be the flow rate of that feed, that will be F, and what will be the output from that, it will be D and also B. Now very interesting that before going to that material balance, you have to fix it up that boundary of that process, based on which that you can do that material balance. Now overall material balance, to do that you can give this boundary you can of that whole processes, that is denoted in blue dotted line here in the slides, and based on which you can calculate. Now if you know that F value and if you substitute that F value as per problem, then you can say this will be equal to B plus D, but this B and D is unknown to you. B is for bottom product and D is for that distillate. Now if you do the overall benzene balance, that means what will be the amount of benzene in overall, it is going to the distillation column, and also overall what will be the output of that benzene product, it is coming out from the distillation column. Now from this boundary of this blue dotted line, you can say that some input of that benzene will be equal to F into XBF. What is F? F is the feed rate, and XBF is that that mass fraction of the benzene in the feed stream, and B is the bottom product flow rate, and XBB is nothing but that mass fraction of benzene. This B is benzene, small b is benzene, and here capital B is for bottom product. So it will be mass fraction at the bottom product of that benzene, and plus D into XBD. D is the distillate flow rate, and XBD is nothing but that mass fraction of that benzene in the distillate stream. So we can have this total amount of benzene is going to that system, that is in the distillation column, is simply F into XBF. And what will be the mass of that benzene is coming out from that distillate and from the bottom stream, that is that you have to add it up. Now from that bottom part, this mass fraction of the benzene is, if it is XBB, it is unknown to you. So it can be that calculated as B into XBB, and in the distillate stream that amount of benzene that is coming out, that will be equal to D into XBD. So from this material balance you can write this equation. After substitution of these F value, it is given to you as in your problem, and the feed benzene fraction is given as 0.4, that is 40% benzene, it is given in the problem. So we can write this equation here, and then you do not know the amount of B, but you know that in the bottom product the benzene mass fraction is given as that 2%. So it will be as B into 0.02. Similarly in the distillate product, you will see that there will be mass fraction of benzene is 97%. So we can write simply that D into 0.97. So from this equation you can have this that based on that mass fraction of benzene in the bottom and distillate product and also in the feed streams, then you can write this equation here. Now you got one equation from your overall material balance like this, and another equation you got overall benzene balance as like this. Now if you solve these two equations, you just see that two equations, what you will see, that you will see that two unknowns are there, B and D, and also two equations are there. So simply you can solve these two equations, and after solving we can get this D will be equal to 5448 kg and B will be equal to 8172 kg. Okay. So what will be the amount of D, what will be the amount of B, simply you can calculate now. Now after that, the problem is that what amount of liquid that will be that sent back to the distillation column as a recycled stream, that you have to calculate. Now if you consider the system unit, or you can say process unit, as a condenser, and they are if you do the material balance, you will see that what should be the inlet and outlet from which you can calculate the what will be the unknown value of liquid there, that is coming into the distillation column. Now, if you do the balance, material balance around that condenser, we can write here again, if you do the overall material balance around this condenser, we can write this V will be equal to L plus D. What is V? V is actually amount of, that is vapor mixture, it is coming out from the distillation column, and after that it will be condensed out, and then it will be coming out as a liquid stream there, and some portion should be sent back as a liquid here. So, in that case we can write here V, that will be equal to L plus D. So, this is input and these are output there. So, simply we can write V is equal to L plus D. Now, if you substitute the value of V, V is given to you, and D now you have calculated from here. So, it is 5448, but here this, what is the value of L here? L is given here that it should be some fraction of D. So, that fraction may be, you can say that it would be equal to D, some fraction it is regarded as R, that is called recycle fraction, and then that recycle fraction, if you multiply with that distillate, you will get that what will be the amount of recycle is coming to that distillation column. So, in that case we can represent that L will be equal to what? D into R. Now, this R is called recycle fraction, or you can simply, it is denoted or you can say it is a reflux there. So, what should be the R? From these two equations you can simply that obtain this R will be equal to this. So, it will be around 1.15. So, in this way you can calculate that what will be the recycle stream and what is its amount, and how to do the material balance. So, here very important that you have to do the overall material balance first of all for whole system, and after that for the recycle portion from where that fluid will be recycled, that unit also you can do the material balance, or you can say that recycle amount where actually it is going to insert as a feed in a process unit, there also you can do a material balance. So, from which you can easily solve the problem for that recycle amount. Let us do another example with bypass stream. Now, here in this case see one schematic diagram of the process. There you will see that some slurry as a mixture of solid and water as a slurry, some amount it will be passed through some mixture. So, some amount of solid and some amount of water will be poured into a that mixture, and from which some portion of that slurry it will be sent to an unit that is called evaporator, and there that slurry will be evaporating, and there that water moist water it will be that evaporated out, and then you will see that slurry will be more thicker and thicker whenever water will be coming out from that evaporator, and after that from that evaporator with a certain degree of thickness of that slurry system, it will be sent to a mixing unit again, and after that some amount of that slurry will be taken out. After that you have to analyze what should be the solid amount with along with that water there. And in this case you will see that whenever you are sending that slurry before entering to that, or before allowing it to the evaporator, you can send some amount of slurry just skipping that evaporator directly to that mixing unit here. So, from this here you can say one divider you can use, and from that divider some amount of slurry will be sent to the mixing unit just by skipping of this evaporator there. and some fractions that will be directly sent to the evaporator, and after that removing of moisture or water by that evaporation, you will see that slurry will be again sent to the mixing point there. So in this case very interesting that that slurry, whenever it will be sent to that evaporator, after evaporation some amount of water will be removed by that evaporation process. Now before going to that evaporator, that slurry contains maybe will be some amount, there may be some fraction of solid particles and some fraction of water. So that is given here. At the inlet has a basis of 100 kg of suppose slurry, which contains 12% of that solid and 88% of water per kg of that that basis, and it will be used to that evaporate by this that evaporator, and from that some amount will be sent directly to that evaporator, and some amount which is some composition here like this, it will be skipping that evaporator and it will sent to the mixing point. Now this this M1 amount to that fraction of that slurry, the same fraction of that slurry component will send to the evaporator and bypassing to the mixing point. Now after evaporator you will see that composition, that is a fraction of that component like solid and water will be changing because of their that evaporation of water from the evaporator. So after that you will see that that amount will be as M4, and that fractions it will be changed, that solid fractions will be coming as 58%, whereas it was earlier only 12%, and water will be as 42%, whereas it was earlier before that evaporator it was 88%. And then this stream from that evaporator, again it will be sent to the mixing point and it will be mixed with that bypass amount that. So after mixing of that outlet stream of the evaporator and the bypass amount, you will see that again that composition will be changed. So in that case composition of that solid will be 42%, whereas water will be 58%, and the amount will be here only M5. Now based on this problem you have to do the material balance and you have to find out the unknown value of streams of like here that is denoted by M1, M2, M3 and M4, and also what is that M5. So in this way you have to calculate. Let us do that calculation here. In this case you will see that first of all you have to do that overall solid balance. Here S means solid. So if we do the solid balance, you will see that in inlet condition that what will be the solid in. So there it is 0.12 into 100, whereas at the outlet of this whole unit, that is outlet, if we denote this here as a that boundary of this system. Now across this boundary we can do that material balance of solid like here 0.12 into 100, that is in, and out only here from this mixer and also from this here, but from the evaporator there will be no solid out as an overall system. So in that case it will be 0. So only this as a M5 streams, that M5 they are only 42% of solid is there, so we can write 0.42 into M5. And also if we do the overall mass balance there, so we can say that 100 kg of slurry is going to that system, and only M5 and M3 kg of that component will be coming as a whole from that system. So then we can write simply 100 will be equals to M3 plus M5. Now if we do the mass balance on this mixing unit, on this only mixing unit, here we can say that only this inlet is M4, outlet is M5, and also inlet again another inlet is M2. So here 2 inlet and 1 outlet is there. So, according to that what would be the solid in and what would be the water in, and what would be the solid out and what will be the water out, that you have to consider. So, in this case if we do the solid balance over this mixing point, what will happen, that we can say that 0.58 into M4 plus 0.12 into M2, that is M2 as a bypass amount, that will be equal to 0.42 into M5. So, we are getting these two equation here again. Now, if we solve this equation number 1 and equation number 2, then we can easily get that you know that 100 will be equal to what, that M1 plus M2. Again bypass balance, if we do that bypass balance there, we can say that 100 will be equals to M1 plus M2. Now, if we substitute that value of M1 and M2, then we can say that after solving, all these M3, M4 and M5 will be coming out. Or based on this equation here, all those equation number 1, 2 and 3, 4 and bypass mass balance also here, you can easily solve these problems for that M1, M2, M3, M4 and M5 there. This way you can do either way also. You can do that first material balance of bypass and then material balance of that only, what is that evaporator, and material balance of that mixing point separately there. So, you can easily calculate what should be the M1 to M5 there. Instead of solid balance, you can do the water balance also. In that way also you can solve this problem. So, same amount of this stream of M1 to M5 you can get. Now, what should be the bypass fraction? Now, bypass fraction is defined here. What would be the input to that bypass and what would be the amount that is coming out from that divider here as a bypass. So, that is simply M2 divided by F. Here M2 is actually, this is 9.95 kg as per solution of these equations, and then input F is 100 kg. So, you can simply say that bypass fraction will be equal to M2 by 100, that means here 0.0995. So, you can that easily then calculate for the multiple unit and with that bypass how to do that material balance here. Now, let us do another example with Purge. Now, suppose a fresh feed that contains 55 weight percent of component A and 45 weight percent of B, that flows at 100 kg per hour and enters to a separator which will remove a portion of your component A only as a bottom product, and the top product stream of the separator contains only 10 weight percent of the component A, and the balance is B. A small part of that separator product stream is recycled and joined in the fresh feed stream, but some other portion is to be purged. Now, the separator is designed to remove exactly 2/3 of the component A that is fed to it, not the fresh feed there. The recycle loop is used to achieve this goal. Now, you have to calculate all unknown streams, flow rates and compositions there. Now, according to this problem, you can draw the flow chart like this here. Here you see that there will be some mixture, and in this mixture feed stream is coming with the component A and component B with a certain fraction, and then it goes to the separator, and from the separator two products will be coming out. One will be from the top, another will be that from the bottom. Now, from the top portions you will see that some fraction of that top portions will be taken out as a purge, and some fraction will be sent back as a recycle to this mixer. Now, this is the problem. according to the that value given in your problem, you have to do the material balance. First of all, you have to the total material balance or overall material balance across this system boundary that is defined by this here red dotted line. Now if we consider that boundary, and in this boundary what is coming in and what is coming out from this boundary. Now in the boundary the amount is coming here as a whole 100 kg, whereas the amount is coming out from that boundary as here suppose M4 and here as a M6. Here M4 and M6 rate are not given to you. Here it is denoted or it is assumed that it will be only M.4 or M.6, that is rate dot means here rate, that means in the stream 4 what will be the rate that is coming out, that is M4 dot, or then in the stream 6 it will be M.6. So overall balance or total material balance, we can say it can be written as 100, it will be equal to M.6 plus M.4. Now you have to do the component balance or component material balance. Now in this case, if we consider component A, you can do that component material balance of A. Now in this case we can write what should be the amount of that is component A is coming into the that boundary of this system. That will be equal to simply 100 into, that is here A is 0.55, so 100 into 0.55, and what is coming out from this boundary only for A, it will be that M.6. Here since it is pure A, all the fractions will be as A, that means 100% A. In that case the fraction of that A will be 1. So here we can directly write here M.6 into 1, so it will be simply M.6. And then from this stream 4, what is the amount of that component A is coming out. Since here the mole fraction or mass fraction of this component is given as 0.1, then we can simply write the amount of A is coming out from this stream 4 will be equals to 0.1 into M.4. So based on this we can write this component material balance here as 0.55 into 100, that will be equal to M.6 plus 0.1 M.4. Interestingly, in this problem there is no reaction is going on and the process is steady state, so we can simply consider here input will be equal to output. Now from these two equations you can solve for M.6 from the overall balance equation like this. Here 0.55 into 100 and M.6 will be equal to what? From this equation you can directly write here 100 minus M.4 and then just simply write 0.1 into M.4 simply. So by these two equations you can write here this equation, and solving here this equation we can simply calculate what should be the value of M.4 here from this equation. Once you know that M.4 from this equation, you can easily find out what should be the M.6 from your total material balance equation. So it is coming here M.6 will be equal to 50 kg per hour and M.4 will be equals to 50 kg per hour, both are same. So in this way you can easily calculate what should be the amount of purge that is taken off from the system. So you had to calculate this bypass amount of M.4. So simply, so this is the simple example of doing the material balance for the purge. Again there are some other streams that you have to calculate based on this problem. If you want to find out that other streams and what are those amount, and then you have to do the material balance for that other systems there, and in that case if we do the material balance for this that unit separator, and if we specify here the boundary for this system, then what is the in and what is the out from this boundary, that you have to now consider here. Now accordingly you have to write the material balance here. Here if we consider this separator, this input is M2 and output are that M6 and M3. So we can simply write here M2 will be equal to here 50 plus M3, because here M6 is 50, that we got earlier. And then if you do the component balance A again for these streams, then we can write here MA at this streams 2 into M dot 2, that will be equal to 50 plus M dot 3 into 0.1. Here in M3 that component A will be equal to 10% according to the problem, and this M dot 6 here, since it is a pure component A, simply it will be into 1, that is fraction will be equal to 1. So simply that means here 100% will be the pure component A here. So accordingly you can write these equations. Now one condition is there, that separator that will remove 2/3 of F head to it in the bottom stream. So in the bottom stream they told that this component A will be 2/3 of A that is fed to it. So in that case we can write here 2/3 of that XA2 into M2, that will be equal to M dot 6. So that will be equal to 50 kg per hour, which implies that XA2 into M dot 2, that will be equal to 75 kg per hour. Now if we do the material balance and material balance for the component A, that already done here. Now if we use this equation and substitute the value of MA2 into M2 dot here, then we can simply write this equation from that equation here. Now from this equation then we can easily calculate what should be the M dot 3. So M dot 3 will be coming as 250 kg per hour. Now if we substitute this M3 as 250 kg per hour into overall mass balance equation around the separator, then we can write here M2 dot, that will be equal to 50 plus M3 dot. That means here it will be equal to M2 dot will be equal to 50 plus 250, then M2 dot will be equal to 300 kg per hour. And then what will be the XA2? XA2 will be equal to here again from that equation earlier. So simply we can calculate from this equation. Now again if we consider that split, around this split, if we do the overall balance, we can write M dot 3, that will be equal to M dot 4 plus that here that will be equal to M dot 5. So we can simply write that here it will be M dot 5. So here we know that M dot 3 will be equals to 250 and M dot 4 is equal to 50, and then remaining M dot 5 will be there here. So that M dot 5 will be equal to 200 kg per hour. So in this way we can do the material balance for that bypass, recycle, parts, and also that makeup also. So in this way we can do other exercise problem also. We will provide some exercise problem later on after finishing this course, and during that run of that course we will give some supplementary materials for the practicing, and then you will practice, and and you I think will that have more idea about that that input and output and material balance, how to do that, all these things. So thank you for your attention. Here I would suggest you to follow that textbook of this given here in the slides for further calculation and also practicing the problem. And the next lecture we will discuss something more about that material balance that will be on reactive processes. Thank you.